All right, thanks. I'm going to continue on the subject of quenching that we have going on here, and particularly the environmental impact on that. People at the CANDELS meeting, some of this material will be the same, but some will be different. And so it's up to you to pay attention to see where the changes occur. I may have updated some of the plots. But mostly I'm going to be talking about work done by my graduate student, Nancy Kawanwanachanakic. She'll be finishing up this year. She is back visiting family in Thailand, or she should be here giving this talk. And so instead I'm going to do my best to talk about her work. Many of it's fantastic, and you should, if you're looking for a postdoc or looking to host a future fellow, you should contact me or her about this. She'd be happy to put you in. I'd be happy to put you in touch with her about that. Okay, so we're gonna. One of the goals here is to understand galaxy quenching, understand these environmental impacts. I'm gonna start with some introduction about that, and then move into what we're doing with it. Here is just to put everybody on the same page. There's a well-established star formation rate density relation, and we know it exists out to redshift of 2 or so. Here's a paper by Ryan Quadri where they studied the star formation rate density relation using what I would consider relatively shallow data back from 2012, so the effects are on relatively massive galaxies. And the point that we'll draw from this is if you just plot up the fraction of quenched galaxies as a function of the density, which we're going to use as a tracer of environment, not only do, as you go to lower redshifts, does the quenched fraction get greater, but the quenched fraction also increases with environment. This is one of these trends that is well established and well known for a while. This builds on other work, well, a very famous now paper, a seminal paper by Peng, Lilly, and collaborators using data from Cosmos and data from the Sloan Digital Sky Survey, where they also studied the effects of both mass quenching and environmental quenching on galaxy evolution. And they find the following, just to take some points out of their abstract, I'll highlight them here. They say there are these two effects. One, we know galaxies quench as they become more massive, as the quenched fraction of galaxies is higher as a function of mass. Two, there's an effect with an increasing environment, and these are completely separable up to redshift of 1. This is the claim they make. And what they mean by that is, if you look at the efficiency of quenching, meaning the excess over some baseline, and you plot that up here, this is the quenching as a function of mass quenching efficiency as a function of the environment, these lines are relatively constant. And each one of these lines is a different bin in log stellar mass. So you have the most massive ones up here, and then you have the lowest mass ones up here. And when you take out the environment, that's a relatively constant fraction. And this is what they saw up to redshift of 1. The same can be plotted if you plot this environmental quenching, now the environmental quenching efficiency as a function of stellar mass. So you take the other axis. And so galaxies in the highest density have the same relative quenching as a function of their environment, and the same moves along here. It's independent with respect to stellar mass, and that's the point they're trying to make, is that these two plots, these effects are separable. Now there are lots of theoretical reasons that this should break down as you go to higher redshifts and for lower stellar masses, and so we wanted to explore this using our own data. One other way this is going to have an impact is on the stellar mass function of galaxies. So here's also looking at this paper from Peng et al., where they looked at this from Sloan Digital Sky Survey, where they separate the stellar mass function into star-forming galaxies and quenched galaxies, and then they separate that further into divisions of density, where they put the highest density galaxies here as triangles. People in the front row can probably differentiate that, but that goes along here. And the lowest density ones as diamonds, where the totals then are up on the top. Looking at the star-forming galaxy stellar mass function, they found there was no difference really in the shape. There might be in the normalization, but not so much in the shape. Star-forming stellar mass function is the same for different environments. For quenched galaxies, they actually find there is a difference in the shape. They seem to have the same sort of exponential cutoff proportion, but there's an increased number density of low mass galaxies in the higher density environments. That's something they found. And we're going to explore this as well. There was a follow-on paper by Bolzonella et al. Who looked at this and interpreted this as taking star-forming galaxies in the low mass population, quenching them, and then producing this tail. And they concluded there was a delay of the quenching time scale of about 2 billion years between redshifts 1 and 0.2 in order to explain this difference. Okay, so we're going to use these as benchmarks against which we can compare galaxy evolution as we go out to higher redshifts. And to do that, we're going to use a couple data sets, but I also wanted, this is a point that Avishai has made to me, and I want to make sure we're all on the same page. We're going to use some nomenclature here when we talk about quenching. The observables we're going to use in our study are the stellar mass, which is simply the luminosity of a galaxy with some correction for its mass to light ratio that we derive from spectral energy distribution analysis. So anything we correlate with this is really a correlation with stellar mass. So when I talk about mass, this is the observable that we make. We're not trying to connect it to halo mass. That would be another layer of analysis. We're going to compare that then with something we call the environment, which is the local density of galaxies, and we're going to make that based on how we measure the surface density, the local surface density of galaxies as well. So this is to keep with other studies in the literature where they use something called mass quenching, and we're going to use that as well. And this is a quenching process that is internal to the galaxy, and it correlates with stellar mass, because that's the measurement we're making. And then we'll separate that with this environmental quenching measure, which we'll say is an externally driven quenching process that scales with this local surface density of galaxies. Now, as Avishai has pointed out, these may be very related, where you can imagine that mass quenching is related to the halo mass growth of the galaxy. And so for a central galaxy, its halo dictates whether or not it will be quenched. And for a satellite galaxy, its fate in environmental quenching may also be related to that halo mass of the central, so that when it becomes a satellite, the exact same physics applies to it as applies to the central galaxy. So these may be related, but in order to compare them with the observations, we're going to separate these two, simply because this is what we actually measure, the stellar mass and the surface density of galaxies. To do that, we're going to use two surveys. One of them is, they both take place in the CANDELS fields, where we have imaged very deeply, fainter than 25th magnitude in the K-band, with something called Z-Forge. It uses the Magellan 4-star imager, where we have used medium band, deep medium bands that split the well-known observing windows in the J-band, the H-band, and the K-band. The J-band is in 3/3, the H-band is split in half, where with these medium bands, going very deeply, we can now isolate the location of galaxy 4,000 angstrom Balmer breaks very precisely, and that allows us to derive very precise photometric redshifts on the order of about 1% or so, all the way out to redshifts of 4. That corresponds to a velocity precision of around 3,000 kilometers a second, and Nancy, my student, has done an incredible job in the paper demonstrating that you can recover very accurately structures statistically using data of this quality. And because we go so deep, we go all the way down to stellar mass limits of around 10 to the 9 at redshifts of 2 or so. We'll combine this, because we're in the CANDELS fields, with the rich morphology that is available from HST. This is just an example to show you that, yes, we have deep HST data. We can measure structures from that. We can measure sizes, surface indices, which we've been hearing so much about today already. Okay. Nancy has used a very nice statistical measure to derive overdensities. It's based on the third nearest neighbor approach, which is a technique that's very standardized. And so this is a Bayesian motivated method that was developed actually by Isovich and then employed by Cohen and Isovich in a nice paper that I don't think gets enough recognition, where instead of just using the distance to the third nearest neighbor, it takes into account all the distances of neighbors up to the third nearest neighbor. So it measures the distance to the first nearest neighbor, second nearest neighbor, and third nearest neighbor. And it's been shown in this paper, and we also did some tests ourselves, to show that this is a much more robust measure of the local density compared to other traditional measures that don't employ this, just because you're taking into account all the measurements of galaxies up to your nth nearest neighbor. And so by doing this, she applies it to the data set, and then she groups the data into quartiles following the what was done in the Pang et al. Paper. This plot now shows the well-known UV, VJ color plot where quiescent galaxies sit in this polygon, and we've separated it into galaxies that are in the lowest density quartile. So these are galaxies that sit in the lowest environments, and ones that sit in the highest environments on this side. So this column is highest density quartile. This is lowest density quartile. The top row shows lower mass galaxy populations between 10 to the 9.5 and 10 to the 10.2. And the bottom row shows galaxies in a higher mass spin. And already you begin to see well-known differences arise all the way out in these massive bins, where for the higher mass populations, you see a well-populated red sequence and a well-populated star-forming sequence. Some of this may be going away as you move out to the higher density regions. As you go to the lower masses, you immediately see that the red sequence is apparent in the highest density quartile, but it almost disappears entirely at lower densities. So again, we're already seeing this well-known established star formation rate density activity exists, but there is some indication that this is persisting even to the lower masses. Nancy has then plotted this in another axis, which is showing here the stellar mass relation along this axis as a function of the overdensity on the y-axis. So up here are the higher density objects, and the lower density objects here are lower mass galaxies, higher mass galaxies. And we've done it in 3 different stellar mass bins. The color coding on here shows the quiescent fraction of galaxies, where the redder colors are very high quiescent fractions relative to the bluer colors, which are the relatively star-forming fractions. And you can see right away, this is a typical trend, that as you increase in stellar mass, galaxies become more quenched, statistically on average, and that persists at all redshifts. You also see that as you increase in overdensity, you find galaxies are also more quenched. And so we can see these two variables on here. What happens is, though, when we plot, we can now use these to compute both the quenching efficiency as a function of mass at fixed environment, and we can compute the quenching efficiency as a function of environment at fixed mass and see how they evolve with redshift out to redshifts of 2. Nancy's done this. Here, this is now showing the stellar mass along this axis against quenching efficiencies, both for the mass quenching efficiency in green diamonds and also for the environmental quenching efficiency in red squares. We'll look at the mass quenching efficiency first. It appears to have a very similar shape at all redshifts, going from relatively low redshifts up to relatively high redshifts. Has the same shape, but overall galaxies become more quenched with time. They just simply quench. So mass quenching appears to have the same level of efficiency as a function of mass for all different redshifts. The environmental quenching efficiency at the lowest redshifts seems to be relatively flat, and this is similar to what Peng et al. Produced in their 2010 paper. Except they were limited at redshift 1 down to relatively high redshifts, relatively high masses because it was a spectroscopic survey. Here we see that extend, there is perhaps a drop at the end. This is at a log scale, so this is about 10, a little over 10% quenched, where this is about 30% quenched up here. What happens as you go to higher redshifts, though, is that this decreases noticeably. So here we see we have relatively high quenching fractions, but here it drops immediately for the low populations. And by the time we're at the highest redshifts, we find almost no quenched galaxies in any environment. So the conclusion to take away from this is that the environmental quenching efficiency correlates with the stellar mass. So whatever's doing the quenching also has to correlate with stellar mass here. Okay, I'm going to come back to this plot quickly and move along. This is the same plot I showed you before. We show the quenched fraction as a function of overdensity and stellar mass and different redshift bins. We can plot this also as the average CERSIC index of galaxies in the same diagram. So instead of showing the quenched fraction, we show it against CERSIC index, and there's been a lot of previous work, much of it from the CANDELS team, that has shown that the CERSIC index is a very strong predictor of what the quenched fraction, and we see that. You see at first glance, these two plots look very similar, until you look closer and you realize, well, here actually, at the lowest masses, for example, as I increase my density, the CERSIC index does not change as fast as the quenched fraction does. We looked at that and saw that qualitatively. We made another plot of this where we actually take the quenched fraction here, and we take the ratio of that to the change in the CERSIC index, and we plotted that here. This is simply showing you that quantity. This is not a physical quantity, it's just to show you how fast these two variables are changing. So here we have the quiescent fraction divided by the CERSIC index in different bins of mass. These are for high mass galaxies along the bottom row and for low mass galaxies along the top row as a function of the overdensity. So looking at the high mass galaxies first, we see that this ratio, don't worry about the numbers, they're almost meaningless, but they are very constant as a function of overdensity. So as high mass galaxies change their quenched fraction, they change their CERSIC index in lockstep as a function of overdensity. For low mass galaxies, that is not the case. It's what we saw before in the other plot, that the quenched fraction changes faster than the CERSIC index as you increase in density. So as low mass galaxies quench, we're seeing that their quench fraction is preceding a change in their morphology. That's all it says here. For low mass galaxies, change in quiescent fraction is faster than the change in morphology. Okay. Now I want to turn my attention to the stellar mass function, and we think we have a picture for how this is the evolution of the stellar mass function is giving us a lot of hints about what's going on with the environmental quenching. Here we're showing the evolution of the stellar mass function as a function of density for star-forming galaxies. And we are taking both for our data, the arrow of time here is actually backwards. Here are low redshift galaxies, and we move up to high redshift galaxies, combining data from our Z-Forge data set with those from the New Firm Medium Band survey, where we've used the same symbols as Peng et al., where the higher density galaxies in the highest densities are in triangles, galaxies in the lowest densities are in diamonds, and all you need to see from this plot is that for star-forming galaxies, the environment makes there's no dependence of the the stellar mass function does not depend on the environment for star-forming galaxies. Now we're going to move on. For quiescent galaxies, we actually see something kind of interesting. Okay, so here we see the low redshifts. We find, very similar to Peng, that there is the higher density population has a stellar mass function with a steeper tail, And for lower mass populations, you see it actually turns over and the slope becomes almost us going down, lower number densities. As you go out to higher redshifts, these changes kind of persist. The higher density stellar mass function sits up here, but you can see very clearly that the evolution of this low mass population is increasing its slope all the way from the highest redshifts we can measure it to the lowest redshifts. What's even more interesting, if you stare at it more closely, in the lowest density populations, yes, we have error bars. We're hitting the limitations of our data with this because we've had to bin the data so much. There's statistically no difference in the shape as you go from the highest redshifts to the lowest redshifts we have here. I'll do this. What I'm going to take is I'm going to take the shape of the stellar mass function in this lowest redshift bin. I'm going to divide all the other ones by it. So I've done that here. So this is taking the stellar mass function for quiescent galaxies and dividing it by the one at the lowest redshift bins. And then we'd apply a constant just to normalize everything at the same stellar mass. Looking at the lowest density quartile now, there's very little indication that there's any change in the shape of the stellar mass function for quiescent galaxies all the way down to the mass limit of our survey, around 10 to the 9 or so. That's for the lowest densities. In other words, there's no indication that for galaxies in the lowest density regions, there does not appear to be any change in the shape of the stellar mass function. Mass quenching may be doing all of the quenching in the lowest density environments. In the highest density environments, we actually see a very rapid evolution in the low mass population. That's what we're seeing here. That this is the relatively low redshift population up here, and it very much agrees with what we see at the lowest redshifts. But as we go to higher redshifts, we see very clearly that the number density of low mass quenched galaxies is dropping very quickly. That's the indication of quenching due to environment. Richard, how are we doing on time? Oh, great. Okay, so we're doing just fine. Okay, so what does this all mean? So here, one thing we can do is, and this is hammer this point home, I'll illustrate this, is we can fit models of Schechter functions to these different stellar mass functions. I'll illustrate that here. This is for a ZForge data set between redshift 0.5 and 1, where we have the highest density. This is for quiescent galaxies in the highest densities here. This is for the quiescent galaxies in the lowest density regions here. We fit Schechter functions. We get constraints both on the characteristic mass of the stellar mass function and also on the low mass slope. Here's the lowest density contours. The highest density has a higher, a steeper slope. Sorry, excuse me, a shallower slope. And as we move, what you find then, you can begin to plot up how these things evolve. Here we see the phi star. This is just the normalization of it, and as time goes by from high redshift to low redshift, we see an overall increase in the number density of galaxies. That's boring. That just tells you that galaxies are becoming more common. Let's instead look at the shape parameters, which are the characteristic stellar mass and the low mass slope here. The triangles are galaxies in the lowest density quartiles, the ones that are in the lowest density regions. And all you should take away from this is that M star does not appear to evolve for those within the limitations of our data. These are the uncertainties on there. Similarly, the low mass slope shows very little evidence of evolving at all in the lowest density regions. In contrast, galaxies in the highest density regions evolve quite substantially. M star seems to increase from the highest redshifts to the lowest redshifts following the diamonds now. And alpha also becomes steeper as we go along. Now, one more step you can see is the squares on here show the total stellar mass function evolution for quiescent galaxies, regardless of environment. And that seems to be matched mostly by the highest density regions. So you can take away from this that the shape evolution of the quiescent stellar mass function is driven entirely by environment. It's dictating what's going on. That's all it says here. All the evolution, the shape of the total quiescent galaxy stellar mass function is a result of environmental quenching. Okay, so what do we think this means? So now we've got this idea that that what it implies, and this would be very different, it'd be telling a very different story if the environmental quenching was constant with stellar mass. Remember, that's what Peng et al. Found, at least for high mass galaxies, that the environmental quenching was independent of stellar mass. And if that was the case, you'd have very different evolution of the stellar mass function. Let me illustrate that here. This is our quiescent galaxy stellar mass function in the lowest density regions at a redshift of 0.5 to 1. It's right here. We can do this is not even a toy model, this is a very simple thought experiment, that if we take this stellar mass function and we add it with some fraction of the star-forming galaxy stellar mass function, and this doesn't evolve at all, so you can use either the high density or the low density ones. So at any given time, if some fraction of these galaxies are quenched and are added to the quiescent galaxy stellar mass function, because there are so many more of these, you would expect the shape of the stellar mass function of the quiescent galaxies to mirror that if that quenching is independent of stellar mass. And that just can't be the case. So you can do that. You can say, okay, let's take this stellar mass function, multiply it by an efficiency that is constant in stellar mass. It would look like this. This is the value found by Peng et al. And you would get a stellar mass function that should look like this solid line through here. It should mirror the shape of the star-forming stellar mass function, which is just simply does not. The data do not support that. Rather, you have to use a mass-dependent environmental quenching formalism that depends on the stellar mass. It's lower for lower mass galaxies. And when you take this stellar mass function, multiply it by this is what's actually found in Nancy's paper, you reproduce this line here. And so in order to reproduce the shape of the quiescent galaxy stellar mass function high redshift, you must have an environmental quenching mechanism that depends on stellar mass. This is at redshift 0.5 to 1. The situation is, I just want to point out, this is only down to masses of 10 to the 9 or so. There's some indication that perhaps it does turn up to mirror the shape of the star-forming stellar mass function at lower masses. And so it may simply be we're seeing evolution with time. We are only sensitive to this down to our mass function stellar mass limit of 10 to the 9. Okay. This is the situation of redshift 0.5 to 1. The situation is even worse at higher redshifts. This is 1 to 1.5, where this is the stellar mass function we find. And but the shape here does not evolve substantially. So if you apply a constant environmental quenching, you would expect many more lower mass quenched galaxies that we just don't see above redshift of 1. So the stellar mass, the environmental quenching efficiency must change with stellar mass at higher redshift. Okay, what does this mean? There are some models. So we need a mechanism where the environmental quenching is dependent on stellar mass. And there are some here. This is very quick. I'll go through this in my last minute. One such model, I don't want to say this is the only model, but this is one such model, was introduced in a paper by Sean McGee and collaborators in 2014, and he calls it overconsumption. And it works sort of the following way. We have here a central galaxy that perhaps is already quenched inside some halo, and it has different mass star-forming satellites nearby it, and they are constantly accreting gas from the IGM. As they fall into this halo, some magical mechanism that theorists here will tell me about later, I have no doubt, stops that accretion. The shock heating, what have you. So as these galaxies fall in here, their accretion mechanism ceases. However, they have their own supply of ISM that they've brought in with them, and they continue to form stars and convert their interstellar gas into stars at the current star formation rate they have it. They just don't have any more accretion. This star formation then begins to drive outflows at the rates that are easily calculable. Then the third step of this model, what happens is the higher mass satellites, because they have higher mass, they have higher star formation rates. Remember, there is a star-forming stellar mass main sequence. The higher stellar mass satellites have higher star formation rates, which drive higher gas ejection rates. And this leads to a shorter gas consumption time scale. But the combination of the higher star formation rate and driving these outflows at higher rates leads them to consume or eject their gas on a shorter time scale than does for lower mass galaxies. And so as a result, you end up with the higher mass star-forming satellites running out of gas sooner. They simply eject it or they consume it faster than their lower mass cousins in here. And this naturally leads then to a model where the quenching mechanism would depend upon the stellar mass of the satellite. This McGee et al., and there's another paper by Ballo et al., they show this is simply the consumption time is a function of mass, and it's much shorter for these higher mass satellites in this model. These are various loading factors for the way the star formation rate couples to the ejection mechanism. Okay. And it's much more effective, they argue, in the past above redshifts of 1, where we need it to be, simply because galaxy star formation rates in general are higher. Okay. So with that, I'll put up my conclusions. I'm going to run through it. One of the ones I really want you to remember is that the environmental quenching mechanism must depend on stellar mass above a redshift of 0.5. It's maybe quasi-constant at lower redshifts that we think that this might be the case, but if this was not true, then the stellar mass function evolution would look very different than when we aspire to. We simply need an environmental quenching mechanism that scales with stellar mass above a redshift of 0.5 or so. This favors models that will scale with stellar mass. There is one, this overconsumption model that I've mentioned on here. And I also want you to remember that the environmental quenching also appears to change these morphologies in a way that we find very interesting. But I don't have enough time to talk about that. Okay, so I'll stop there and take any questions. Thank you. Yeah, just yell. Yeah, I think that's the case. So you're saying, like, is there a way that the higher mass galaxies simply have lower gas fractions initially? I think that's also fine. So it doesn't need to be, it doesn't necessarily need to be coupled with these faster ejection rates. It simply would be that, but the point is when they fall into the halo, they're stuck with a fixed gas supply that's no longer being replenished. Right. And that leads to a natural explanation, right? Right. Yeah, okay, that'd be great. So yeah, this does not necessarily need to be the only model. In fact, I think this probably makes sense because in the past, star formation rates are overall higher, so these mechanisms would be more efficient, right? Whereas today, maybe ram pressure stripping dominates because these are just less efficient. Yeah. Yeah, right. So you're saying we have not, in the little hocus pocus toy model, it's not even a toy model, it's like, you know, it's a back of the envelope model. We're not accounting for mass quenching, and that's absolutely true. We didn't include that. So that would primarily affect the high mass end of the mass function. If you looked closely, you would see there's some offset. Right. Right. Mass quenching is so inefficient at low masses, it wouldn't do anything you're right. So yeah, absolutely. Good question. Yeah.